Let's check. Hello. Check. Hello.
Hear you guys now. Sorry.
Hello. Check.
Can you hear me okay?
Hello.
No problems.
KT Chennai. KT Chennai. Hello. Hello, sir. Can you hear me now? Hello. Hello. Nishant. American expressions ತನಗೆ ಅಲ್ವಕ್ಕೆ ಲೈವ್ ಡಾನ್ಸ್ ಬಂದಿದೆ ಅದು ಗೊತ್ತೇನು ಇಂಕೋటి ಬರ್ತದೆ అవును ఎట్లు పెట్టారు ఆ బ్లాక్ ఉన్న సిల్వర్ Sir, can you confirm once? Can you hear us now?
I can hear, but quite bleeding.
Perfect, sir.
Yeah. It's great. It's good.
Sir, you were saying something? Hello? Yeah, yes, sir. You said something. Can you hear us? Okay, sir. Okay, sir. So now I'm giving we're shifting you onto the main stage, sir. So like the auditorium is 500 seating capacity, and we are also screening this lecture on YouTube and all to all the Rgukt campuses. Okay, sir. Yes, sir.
Very good morning, everybody. A very warm welcome and delightful day. Welcome you all to the day 5 of the Qiskit Fall Fest 2025, proudly being hosted by Rgukt Srikakulam and sponsored by IBM Quantum. And I hope you all are having a refreshing start to the day, carrying along the same spark that of curiosity and enthusiasm that has been lighting up the entire week. And from decoding qubits to diving deep into the hybrid algorithms, every single day has been a celebration of learning. And I'm so sure about that. And today we continue that journey with even more brilliance. We have witnessed incredible energy, thoughtful participation, and some truly inspiring sessions so far. And that momentum doesn't stop here. Day 5 is going to be the next level one and to be yet another powerful blend of insight, innovation, and inspiration. So let me walk you through what we have lined up for the entire day. We begin our morning with a virtual guest lecture by an extraordinary personality, Dr. Srikant Tudumu, Director of Artificial Intelligence at IAAIR, United States. His work in advanced AI technologies across global domains has made remarkable impact, and we are honored to have him share his experience with us today. Following that, we will be having the continuation of our hands-on workshop on Qiskit, mentored by Dr. Gnan Yala, CTO at datatech.ai, a researcher known for his deep work in quantum machine learning and hybrid algorithms. His sessions have been a perfect fusion of concept and code, and today's continuation promises even more exploration and excitement, and I'm sure of it. And that's not all, guys. We also have an in person workshop by Mr. Tilok Sadhu Khan, quantum computing engineer and quantum developer at CDAC Bangalore, who will be guiding us through the Qniverse platform, helping us translate theory into tangible interactive quantum experience. And post lunch, we'll be having a very special occasion, the inaugural ceremony of the hackathon. We are truly honored to have with us some special delegates to inaugurate that 48-hour long hackathon. A small and huge challenge at the same time that will test not only your technical skills but also your creativity, teamwork, and problem solving spirit. So, gear up, everybody. This is where ideas turn into innovation. And before we dive into the first session, let's take a moment to appreciate the incredible energy you all brought up to this fest so far. The questions, the curiosity, the hands on engagement, it's been phenomenal, really. As we step into today's session, let us continue to learn, collaborate, and challenge ourselves because that's exactly what makes Qiskit Fall Fest so special. And now for the start of the day, I'd like to invite the lead organizer of Qiskit Fall Fest 2025, Mr. Katam Nikhil Teja, to introduce our first special guest today.
Good morning, everyone. It is my distinct honor and privilege to introduce our guest lecturer for today's session, Dr. Srikant Tudumu, Director of Artificial Intelligence at the Institute of Applied Artificial Intelligence and Robotics, United States. Dr. Srikant leads IAAIR's strategic direction, research initiatives, and industry collaborations, driving innovation at the intersection of artificial intelligence and real world applications. His expertise lies in productionizing AI research, turning academic breakthroughs into scalable, high impact industry solutions. With a PhD in artificial intelligence, he has dedicated his career to operationalizing AI into practical domains, focusing on ML model reduction, AI driven automation, and cost efficient AI adoption for business worldwide. Before joining IAAIR, Dr. Srikant served as a senior research fellow at the Applied Artificial Intelligence Institute, Deakin University, where he led groundbreaking projects in collaboration with CSIRO and the Australian Department of Defense. His work includes the creation of a digital twin for a brain controlled wheelchair, a context aware neural search engine, and an advanced image processing platform for merchandise. Innovations that have not only gained industry recognition but also made tangible real world impact. Beyond his technical excellence, Dr. Srikant is deeply passionate about bridging the gap between research and application and continues to mentor aspiring AI scientists, engineers, and researchers across the globe. In fact, I've learned about applied research importance through his work and through their website. We are truly honored to have him with us today to share his insights and experiences at the forefront of applied innovation. Ladies and gentlemen, please join me in extending a very warm welcome to Dr. Srikant Tudumu. Sir, the virtual dais is all yours.
Oh, thank you very much. Can you all hear me? Uh,
Yes, sir, we were able to hear you.
Can I share my screen or should I be just talking?
You can share your screen, sir.
So thank you very much. Let me share my screen. All right. Can you all see my screen?
Yes, sir. Perfect.
Excellent. First of all, thank you so much for that wonderful welcome. So, good morning, everyone. So, it's amazing to see or hear such an energetic crowd here at Qiskit Fall Fest 2025. Even though I'm virtual, I can hear that energy through uh, Nickel and you know from his words. So my name is Srikant, and I currently work as the director of EI, the Institute of Applied Artificial Intelligence and Robotics. And over the past several years, my work has focused on quantum machine learning, hybrid algorithms, applied AI, and building practical systems that bring cutting-edge research closer to real-world applications. So, what excites me the most about this event is that it's just about listening to talks. It's also about building. So it's about exploring new ideas together. So quantum computing and AI are no longer distant concepts. They are kind of rapidly becoming tools we can use today. So I have spent a big part of my career working on applied AI and also on more recently how quantum technologies can push the boundaries of what AI can do and how AI can make quantum systems smarter and more useful. So I think events like this bring together brilliant minds, students, developers, researchers, all in one space, ready to experiment, collaborate, and create. I think through this fest, you'll all have the chance to get hands-on, to test your ideas, and to be part of something genuinely exciting. So, as we begin this journey, I encourage you to be curious, ask questions. You can challenge assumptions, and most importantly, have fun. So, once again, I'm Shrikant, and I'm truly honored to be here with all of you today virtually. Let's make this Fall Fest a memorable one. So let me start my webinar today. So I'll be talking about quantum artificial intelligence. So let me move my slide here. So as you can see, what exactly is QAI? So we call it as quantum artificial intelligence. But what exactly is this quantum artificial intelligence? So um, we are at the juncture of quantum computing and artificial intelligence. So, what do I mean by that? So, let me give you an example. Let's say, okay. So, throughout history, every major shift in computing opened new possibilities. Like if you take mainframes, they made large calculations possible, and personal computers made computing accessible, cloud computing and AI made data-driven applications powerful. Now we are entering another shift. We call it as quantum artificial intelligence. So QAI means combining the learning and reasoning abilities of AI with the special properties of quantum computing. So instead of just making current AI faster, QI, QAI can tackle problems that classical systems simply can't handle well, like large-scale optimization, complex simulations, or analyzing extremely high-dimensional data. So this future will not be purely quantum, it will be hybrid, meaning both classical and quantum computers will work together. And as computer science engineers, will be the ones building the layers that make this possible. So classical computers use bits, as you might already know this stuff, so which can only be 0 and 1. Quantum computers use qubits. I'm pretty much sure you all know what it is about. Qubits, which can be both 0 and 1 at the same time, we call that as superposition. Think of it like a spinning coin while it's spinning. It's not just heads or tails. It's in both states. Only when it lands does it become one or the other. Qubits can also be entangled, which means the states are linked. Changing one affects the other instantly, even if they are far apart. Millions of miles apart. So when we combine these quantum effects with AI, we get algorithms that can explore many possibilities at once. So what do I mean by that? For example, let's take a classical search algorithm looks through options one by one. So a QAI algorithm can look at thousands of options at the same time and collapse down to the best one much faster. And this creates opportunities for breakthroughs in optimization, simulation, and learning tasks. So why QAI matters? Today's AI is powerful, definitely, but also it's very heavy. If you were to train a large language model, it can take weeks on thousands of GPUs, and it can consume huge amounts of energy and electricity and cost millions of dollars. And even with that power, some problems are just too big. Let's take the traveling salesman problem. So if we have hundreds of cities, finding the shortest route requires testing astronomical number of combinations. A quantum system can actually encode all these probabilities at once. Like using qubits, making it far easier to find a good solution quickly. So let's also take another example of drug discovery. So classical computers take months to simulate like how molecules interact because the molecular behavior itself is quantum, as everyone knows. Whereas a QAI system can model all these behaviors much more naturally. And this saves both time and the cost. And this is why QAI matters. It's not just an upgrade, it's a way to solve a different class of problems entirely. So, what exactly are the key building blocks of QAI? Like, think of QAI, quantum artificial intelligence, as a technology stack. And there is a good reason behind why I'm giving this analogy. So, at the bottom is hardware, which is the physical quantum computer you might have seen in pictures like IBM's superconducting systems, or if you take IonQ's trap ion machines. And on top of that, there are quantum algorithms. So, you might have heard of Grover's algorithm for search or QAOA for optimization and all that stuff. So, these are like the sorting or graph algorithms we use in traditional computing, but designed for quantum machines. Right? Then come quantum machine learning models built using quantum circuits such as quantum neural networks. We call it as QNNs. To make these quantum pieces work with classical computers, we use a middleware, which is kind of a software that lets the two communicate between each other. And finally, developers they write code using high-level frameworks like Qiskit or TensorFlow Quantum or something like that. For CS engineers or computer science engineers, understanding this stack is very similar to how we think of hardware operating systems, OS, and software layers in traditional computing. So from QML to QAI. So right now we are right now quantum machine learning is about improving basic ML tasks like classifying data or finding patterns. But QAI basically goes further. A lot of people does argue that QML and QAI are the same, but they are not. So QML is about improving basic ML tasks, as I mentioned earlier, classifying data or finding patterns. But QAI is different. It goes further than that. It's about making AI systems more intelligent, not just more efficient. Let's take an example of reinforcement learning. So, teaching a system to make decisions by trial and error. A classical RL agent, reinforcement learning agent, explores one strategy at a time, whereas a quantum RL agent can explore many strategies at once. So, think of the possibilities because the policies are encoded in a superposition of states. So, let me give you an example. Let's say if you're training a robot, right, to navigate a warehouse, and a classical computer may take thousands of attempts. Let's take a QA system for the same scenario. This particular QA system can evaluate many navigation paths simultaneously, and it can converge to an optimal path faster. Another example I could take is a team of autonomous drones coordinating flight routes. Right? A QAI multi-agent system can optimize coordination in real time, something classical systems struggle with at scale. So, what exactly is the recent progress in quantum algorithms? So, I mean, the field we're talking about QAI isn't just theoretical. There's a measurable progress out there. So, there's something called as variational quantum circuits. They are trainable circuits that very much behave like a neural network layers. And there are something called as quantum kernels, which give classical algorithms access to richer representations of data, making classification and clustering even more powerful. And there is also something called as Hilbert space. Basically, it's like a mathematical space where quantum states live in there. Like unlike ordinary 2D or 3D space, Hilbert space can have exponentially many dimensions. And this is what allows quantum algorithms to represent complex patterns more compactly than classical models. Again, let's take an example. So researchers have already used quantum circuits to classify sentences in a language task. Even with limited hardware, they achieve performance close to classical models, but with less computation. And another team used quantum computing, quantum methods to estimate molecular energy levels more accurately than classical simulations. And we got frameworks such as Penny which let developers combine both quantum and classical ML in the same workflow today. If you're interested in understanding more of this research, so we recently published a paper and we'll be presenting at the 2025 IEEE conference on quantum artificial intelligence the first week of November in Italy, Naples. So if you're interested, it's available in archive. Just Google my name and you can find my recent papers and just go and read it. You'll find it very interesting. So the hardware evolution. So let's talk about hardware evolution. So the quantum hardware today is now very much similar to the early personal computers. Let's go back. Let's rewind back to 1970s. It was, but it is very limited. The main issues are noise, like what you call unwanted interference or decoherence. Like when I say noise, it's unwanted interference. Like you literally have that interference, which you don't want it to have. And then there is something called as decoherence, which is basically loss of quantum information over the time. And then error mitigation is like noise cancellation in audio. It doesn't remove all noise, but it makes the signals more cleaner. This allows slightly larger models to run reliably. So in the next few years, companies plan to scale their machines to over 1,000 qubits. You might have heard of it or you might have read a research paper. So eventually they will achieve fault tolerance, which means the system can run long, complex problems without actually breaking down. So for quantum artificial intelligence, this is kind of a big deal. So more qubits and more stability means more complex learning tasks, like take the problems of large optimization problems of real-time control systems becoming practical. So what happens in the near term, right? In the next 4 to 0, in the next 5 years. In the next 5 years, again, if you want more information on that, I would strongly encourage you to go and read the paper we recently published. We recently published an archives in a preprint, but it's been selected for a conference, as I mentioned earlier. So again, in the next 5 years, we'll see QAI used for targeted high-value problems. For example, airlines and shipping companies must constantly update their routes and schedules. So classical traditional computers, they can take hours to optimize all these processes, especially during disruptions. Whereas the QAI system can evaluate many route options at once and find near optimal solutions faster. And another example I could take is cybersecurity, right? Quantum anomaly detection. By the way, anomaly detection is what I did in my PhD. So let's take quantum anomaly detection. It can analyze massive logs and network flows to detect suspicious activity earlier. And during my PhD, I realized so I've worked on my PhD research area is anomaly detection in high-dimensional big data. And when there are high dimensions, there's a problem called the curse of dimensionality. And detecting anomalies in that particular big data is a humongous, it requires humongous computational power. And we can't even micro manage or micro detect all these anomalies. You can only identify the spaces where there are potential anomalies. If we want to apply this quantum computing in that anomaly detection space, think of how many fraudulent transactions we can pinpoint. Think of how many fraudulent or intrusions in the network we can detect, right? And in drug discovery, there's a problem called drug discovery, right? So you require a lot of computational power. Let's say there is a new disease that comes up, and there are there's a new virus that comes up, right? And there's a lots of research, and there's a lots of research papers, and there's lots of research that's been happening, and there's lots of data in the Excel sheets or spreadsheets, and there's a lots of data in the brain of the scientists. So currently we are just limited. We cannot, see the relationships between all these data sets. They are not fused because we do not have that computational part. And given a virus, understand its DNA and all that stuff, and see what is the best combination to start a research, to start research and coming up with a drug that could actually kill that virus. So now we have to do a lot of things. The data is scattered across various sources. The data is scattered across various places, and there is no relationship. Think of having that quantum computing, and then where it can identify its relationships automatically given the viral structure or whatsoever it is, and then going to these resources, identifying the combinations and relationships, automatically establish the relationships, and then identifying the drug. If we were to have a situation like COVID or coronavirus or something like that, it can potentially come up with a solution even more faster than the usual one, right? Physically, and we can test it physically, and we can reduce the number of compounds that need to be tested, and we can save millions of people or millions of dollars. Let me put it that way. Of course, we need to do all this testing, clinical trials and all that stuff. So, but potentially it can bypass that, the process of drug discovery, and start giving us at least something to test with, and it will make things faster. There is something called as a site feasibility analysis in pharmaceutical industry, where if someone were to come up with a drug, a discovery or something like that, they need to you know. Uh, capture and gather all the data and try to see, the issues that comes with all these site feasibilities and whether the site is useful or not. So all these things can be easily solved. So, and there are something called as recommendation systems, like if you were to use Netflix or Amazon, I believe a lot of people use it. So let's say if you watch a movie or if you buy a product in Amazon, so you got the personalized products, but how many times you realize that it is not your uh, your what you wanted to have, right? And there's also something called as preference falsification. Sometimes in the public, you might say, "Hey, I like this one," but in reality, you might not because of various section of this. When you hyper personalize all these events, is there an AI that could detect without actually spending a lot of time? So quantum computing can actually solve this problem. So you can get products even the moment you think you will get the recommendation, something like that. So quantum computing is that. So that's near-term applications and mid-term applications. So once the quantum hardware gets more stable, applications will definitely expand. Let's imagine a scenario called autonomous vehicles that not only drive themselves but coordinate citywide traffic, right? So let's say here in the states we got autonomous vehicles, they are taxis. So let's say if a autonomous vehicle is going right in one direction and there is a traffic event or something like that, how can it understands there is a traffic problem real time, and how can it be how can it take a take another route or something like that, right? So there's a lots of traffic related issues. So a QAI, let's say if you have a controller that's based on QAI, it can consider thousands of traffic states at once, adjusting its signals and routes, and then it can avoid congestion. And then another example that I could do is a global supply chain, which can be optimized dynamically, responding to factory shutdowns or natural disasters in real time. And in cybersecurity, we have ever heard of quantum cryptography. It will provide data, and quantum cryptanalysis will expose weaknesses in classical systems. And let's take robotics. QI can simulate various robot configurations just like that, and and control policies faster than classical simulators. You can speed up innovation in manufacturing, and that's midterm. So then long-term vision, which is beyond 2035. And again, if you need more information, I always refer to my paper because it's been we gave a good amount of thinking, and then we reported with our lit review. So please go and have a look at that paper if you have more questions. So beyond 2035, we'll see QI not just as specialized tool, but as a core infrastructure. So imagine an intelligent global power grid, right? QA agents monitor energy demand and supply worldwide and adjust flows instantly to prevent any blackouts. Financial systems could use this QAI to detect systematic risks before they even cause crashes, and large transportation networks could self-optimize without the human intervention, without human planners. And at this stage, QAI won't be a separate quantum box. It will be integrated with classical computing systems and human decision-making tools, creating a powerful hybrid intelligence. So, what's the role of QAI in science and engineering? And science and engineering will see some of the biggest gains for sure. As I mentioned earlier, drug discovery currently takes 10 to 15 years. Each drug discovery currently takes 10 to 15 years. That's what I was talking about, and millions of dollars. QAI can actually simulate that molecular interactions in quantum terms, dramatically speeding up early phases of development. And if you were to take material science, which is going to use QAI to find new compounds for clean energy companies, technologies, for example, solar panels or more efficient batteries. If you were to take climate modeling, quantum algorithms can process humongous amounts of data to simulate Earth's atmosphere very precisely. So engineers solving partial differential equations, like you know partial what are partial differential equations? We call it PDEs. They do it for heat transfers and for structures and fluids, right? We can actually use this QAI to speed up those simulations. Even in aerospace, like mission planners, we can use this quantum optimization to minimize the fuel use and risk. So the other thing is the QI in enterprise. So I mean, QAI is not just for for research labs. It will definitely going to reshape industries. Financial institutions can use quantum enhanced algorithms. As I mentioned earlier, we can detect fraudulent transactions much earlier than current systems. And because supply chains like those used by major e-commerce companies, it can react to they can react to supply chains can react to dynamically to disruptions. And as mentioned earlier, hyper personalization recommendation systems can become more personalized without consuming any more computing resources. So QAI can analyze large graphs of customers, products, and behavioral patterns very much faster. And in cybersecurity, again, QI can monitor the network behavior in real time. Blockchain systems can use quantum methods to make verification more efficient, supporting faster and more secure transactions. However, there are some technical challenges for sure. QI has got major obstacles to overcome. So, as mentioned earlier, noise and decoherence make quantum computers unreliable, right? If you were to take for long calculations, they are not reliable. So encoding classical data into quantum states can be very time consuming and sometimes removes the performance gain. We also don't have standardized benchmarks. For example, if you were to take ImageNet for QI, which makes it really hard to measure real progress. And obviously, there is a skills gap too. Not many engineers are trained both in machine learning and quantum computing. I believe this is going to be the future. If we were to work on this space at the juncture of quantum and machine learning, the jobs will be here at this juncture. So if you know a bit of quantum computing, if you know a bit of machine learning, and you start exploring and you become professional, and that's where the future is going to be, and that's where the jobs will be, in my opinion. And hybrid architectures are also technically challenging. Quantum processors work very differently from CPUs or GPUs, which means you need to have orchestration, which must be carefully designed. So, having said all of these things, there are definitely some ethical and societal implications for sure. QAI is powerful, but that power comes with responsibility. If only a few companies or countries control advanced QAI, they may have significant economic or political advantages, right? Let's say quantum cryptography and cryptanalysis will change how security works and possibly breaking current encryption standards, right? And if like QA systems could also behave like black boxes. I mean, you know what is a black box, right? Making it hard to understand how decisions are made. You know it works, but you don't know why it works and who it works, which is very dangerous in fields like healthcare. If you take healthcare, let's say you know if it is working, but if you don't know why it is working, then it's dangerous. And even if you were to take the law, take all the raw files, code files, existing files ever existed and come up with your own analysis, right? And you don't know why it is working. Defense, something is not working. You would have no clue why it is not, right? So that's dangerous. And that's why ethical standards, there'll be auditing systems and transparent algorithms need to be part of QI development from the beginning, not just after deployment. And then research and policy priorities. What do I mean by that? So for QAI, in a sustainable way, research and policy must work together. So let's say we got a fault tolerant quantum hardware, which is essential for stable systems. So open benchmarks will make research reproducible and transparent. Universities and industry need to train a new generation of engineers who can think in both classical and quantum terms. And that's exactly why I'm doing this webinar today. So we need to understand both the realms. It's not just purely classical machine learning or traditional machine learning or traditional computing, it's also quantum. So when you combine together, because in order to be fully realize that quantum computing is going to take some time. So we'll be slowly going there. We cannot just go to the top of quantum computing. You have to take the steps, right? You have the staircase and you have to go through the steps. And I believe that QAI is the staircase. And very initially you have got classical computing, and the more steps you do it, right, will go to the top of quantum computing. So and very importantly, ethics and security must be built it from the start. And this is a lesson learned from AI. We need to apply it early for QAI. So and yeah, that's the projected roadmap for supervised quantum machine learning, and that's coming from my paper. And again, I cannot really go through each and everything, but I kind of explain all these things in a way that you guys understand. And if you want to have more of this understanding, please go ahead and look at my paper, and you will have a lot of more intuition. But if you have more questions, you can find my email ID on top of the paper, and you can always send an email. So sometimes quantum AI is not just an academic area, right? Academic idea. It's a real technological wave. It's building slowly but steadily. As I mentioned earlier, in the early years, QAI will focus on specialized problems like optimization, simulation, and anomaly detection. But over the time, it will become a core computing capability, just like cloud computing is today. For computer science and engineering students, I think this is a rare opportunity. The people who understand QAI early will shape its future. And I'm very glad that you guys are already been doing so. Whether you work on infrastructure, algorithms, or applications, any part of QAI, your role will be very, very crucial if you understand both of these topics. So this isn't just about building powerful tools. It is also about building them responsibly. So QAI benefits society as a whole. So I strongly suggest, like, if you know quantum computing, that's perfect. That's very good. And if you also know machine learning, try to be at the juncture of both of them. So, and yeah, I understand that there might not be, a platform for you all to actually play with, computing, quantum computing. It is super expensive. I understand that. There are simulators like Penny. Just play with some. So one of my interns from Stanford University, we are trying to build a domain-specific language uh, for actually building, talking to penny lane and talking to quantum computing instead of doing all these, you know, wires and entanglement superpositions, understanding all that terminology, technical terminology, which are really low level. What we're trying to do is we're trying to build. So we got another intern from the University UK, and they're doing. These guys are doing amazing job. So if you are more interested, just go and visit our website and see our research and see the intern proposals that we're doing. You're more than welcome to get in touch. That's pretty much it from my side. I hope that helps. Are there any questions? I'm happy to take any questions. Can you all hear me?
Thank you so much for such an absolutely fascinating session, sir. All dear participants, let's show how much we loved this session with a big round of applause to us, sir. Thank you so much for your valuable time and insight, sir. You have walked us through the world where quantum meets artificial intelligence and the space that rapidly shaping the future of technology itself. From the motivation behind quantum AI to its building blocks, the beautifully connected how quantum computing hardware, algorithms, and AI models can together redefine problem solving from just pattern recognition to true cognitive problems and intelligence. He shared his insights into the progress in NASQ systems, the evolving roadmap towards thousands of qubits, and how QAI is already finding its way into science, engineering, and also enterprise. In areas like molecular modeling, material science, logistic optimization, and even financial forecasting. And of course, Sir didn't shy away from addressing the technical and ethical challenges from noise and talent scarcity to the critical need for governance, transparency, and responsible AI innovation. Sir, thank you so much for such a thought provoking and visionary session. Your clarity, patience, and ability to simplify such a complex frontier truly inspired all of us. On behalf of everyone here at RGKT Srikakulam and the entire Qiskit Fall Fest organizing team, we extend our heartfelt gratitude for your time, your insights, and your valuable patience, and also your encouragement towards the next generation of innovators. Let's give a huge round of applause for Dr. Srikant Durmuso for setting such a powerful tone for day 5.
Thank you very much.
And everybody, this is just a short span of break you can have, and then we will be having the hands-on workshop on Qiskit, continued by Dr. Gnan Yala sir. So get ready for more knowledge today.
सिर्फ 10 साल इन्वेस्ट करने पर तुझे मिल सकता है रिटायरमेंट पे 7 करोड़। पागल बना रहा है क्या? हाँ, दैट्स नॉट मैजिक।
And as we are having a little time in between the session, I would like to give you a little heads up about the hackathon guidelines, guys. Whoever is here in person and whoever is watching this event online also, I would just like to share the hackathon guidelines to you. You can also see it on the screen here. The hackathon is a completely 48-hour hackathon, which is an exciting opportunity for students and innovators to explore, build, and then contribute and showcase projects in the field of quantum computing using tools such as Qiskit and IBM Quantum Services. This hackathon will be starting from 2 p.m. on today, which is 25th of October, and it will last up to exactly 48 hours and will end on 27th October by exactly 2 p.m. And participants are expected to collaborate, ideate, and then develop creative solutions to the real world problems using quantum technologies. And let me get to a few rules. Each team must complete their registration through the official portal, which you can access through the quantum.rgukt.in on or before 22nd. I hope most of the hackathon registrations have came in and the registration is also closed. So the hackathon is open to all the registered participants of Qiskit Fall Fest 2025. Every participant must carry their college ID card as well as the registration proofs for the hackathon while coming to the venue. And each team must consist of 3 to 5 members. Every team should designate one team leader, one member of the team as your team lead, who will be responsible for all communications with the organizers. It's like a point of contact. So, teams must report to the venue at least 1 or 2 hours before the hackathon begins itself. You know, there will be arrangements, right? So, all participating teams are also advised to utilize the space allocated to only them, and participants are advised to bring their laptops, chargers, or power backups, or whatever it is like water bottles, books, pens, and other necessary accessories. And internet access will surely be provided for the research and collaboration purposes from our university itself. All participants must maintain professional behavior and decorum throughout the event. This is a very important point. Respect mentors, judges, the jury, and the fellow participants at all the times. All teams must adhere to the official code of conduct also. Harassment, discrimination, or any kind of unethical behavior will lead to immediate disqualification. No specific mentorship or technical guidance will surely be provided to you during the 48-hour hackathon. Participants are expected to work independently as you are intended to and rely on their team's skills and collaboration. However, our support teams will be available throughout the event to assist you with any logistics or unavoidable issues such as connectivity or access or any system related occurrences. So, use of any pre built or external code without proper disclosure and acknowledgement is prohibited. Projects must be developed during the 48-hour tenure of the hackathon itself. And coming to the project and development rules, all projects must be developed using Qiskit or IBM Quantum tools and services. If you are willing to use any other tools, they should be mentioned. Teams may also integrate open source libraries and APIs, provided that proper credits and citations are included. And every project should involve a quantum computing component or a hybrid quantum classical approach. Ideas should aim to solve real world problems or demonstrate innovative applications of quantum technologies. All code, design, and documentation must be created during the hackathon hours itself. Use of pre existing codes or designs without disclosure will result in disqualification. Each teams must submit an initial idea or problem statement within the first hour of the hackathon itself. Any significant change in direction must be communicated to the concerned organizers or the personals who will be available right there. And development must begin only after the official start of the time, which is 48 hours timer, and continue within the 48-hour duration itself. Teams are encouraged to plan milestones to manage time efficiently and track their progress. Every project must include a README file, which is kind of a document describing complete details about your project, explaining the concept, the setup instructions, dependencies, and execution steps. Proper documentation is essential for final evaluation. And teams must upload their final code or documentation and abstract to the designated repositories or the submission portal. And this will be confirmed after the start of the hackathon. We'll announce the detail how we'll be collecting your submissions also. Internet access is permitted strictly for research, referencing, and learning purposes. Direct copying of code or ready made solutions from external sources is not allowed, but without proper disclosure and acknowledgement. If you are doing that, maybe you can use it. And any additional hardware components or integrations must be declared in advance and approved by the organizing committee. Coming to the technical guidelines, the preferred language for development is Python and Java, and other languages such as JavaScript, C++, or whatever it might be. Since Qiskit is supported by Python and Java, they are preferable. Any other languages can be used only if they are compatible with Qiskit or IBM Quantum APIs, which might be useful for developing your projects. Projects must primarily use the Qiskit SDK and related IBM Quantum tools. Participants may access IBM Quantum services either through Qiskit runtime environments or local setup with API access to IBM Quantum benchmarks. And teams may explore the following official Qiskit extensions to strengthen their solutions, like Qiskit Machine Learning, Qiskit Nature, Qiskit Finance, Qiskit Optimization, Qiskit ACR for simulation and testing. Participants are responsible for setting up their own development environment prior to the event itself. It's highly recommended to test your Qiskit installation and IBM Quantum account before entering the hackathon venue and beginning the hackathon. Cloud based computation is also allowed through IBM Quantum Cloud. External tools, APIs, and datasets must be open source or publicly accessible. All dependencies used in the project must be listed clearly in the documentation so that we will be getting a clarity of what you are being using. Each team should maintain version control using GitHub or similar platforms. Repository should be kept private during the hackathon and made public upon submissions. This this point is a little bit tentative. We'll be giving a clarity about how your final submission will be collected during the hackathon. Coming to the time and submission rules, the hackathon will run continuously for a complete 48-hour tenure starting from today 2 p.m. to 27th October 2 p.m. Participants are expected to work on their projects consistently within only this time frame. The entire evaluation process will consist of 5 reviews conducted by the jury panel members. You'll be getting to know the clear review procedure and what you are expected to deliver in those 5 reviews and how you will be awarded the marks for those submissions when you reach the venue. Or you can also go through the document which have been sent to the team leads of the hackathons. The final 3 winning teams will be announced based on the jury deliberation and overall performance. The complete decision will be in the hands of the jury panel. All code, documents, and presentations must be submitted to the official portal before the final deadline itself. We'll be giving you a clarity of how the submission process will be going on. And late submissions will be considered only under exceptional circumstances and that too with prior approval from the organizers. So teams are encouraged to plan their workflow strategically, allotting time for ideation, coding, optimization, documentation, and also the final presentation because that's what says what you are working on and what solution you are giving to the business world. And the judging criteria will be each team will be evaluated by the jury through 5 independent reviews. Every review will cover the innovation of the idea, the technical implementation, relevance to the problem, and the teamwork and effort in solving it. The top 10 teams will be the highest, who are holding the highest cumulative scores following these 5 reviews, will be shortlisted for the final presentations on the dais. And all projects will be evaluated by the jury panel who are exceptionally intelligent in these fields and based on the judging criteria itself. The top teams will be shortlisted for the final presentations and winners will receive awards, prizes, and recognitions. All participation all participants completing the hackathon will receive participation certificates from IBM Quantum and Rgukt-Ap. And I must remind you to behave very well during the hackathon. Treat all participants, mentors, organizers, and even the support team and the jury members with very much kind respect and generosity. Encourage teamwork and constructive collaboration within and across teams also. All projects must be submitted as the original work of the team itself. Plagiarism, copying, or using unpermitted external solution solutions will lead to disqualifications. Mostly all the AI use and internet access is being provided to you. So you might not come to use this external solutions which are not allowed. I hope you will be aware of it. And avoid any behavior that disrupts the hackathon or causes inconvenience to others. Harassment or offensive language or inappropriate actions will also never be tolerated. Participants must be provided resources responsibly and adhere to any equipment or software uses rules also. Respect shared workshops and facilities while you're at the venue. Follow all the instructions provided by organizers and the jury members. All teams, communications, submissions, and presentations must comply within the hackathon rules and the guidelines. Violations of the code of conduct may result in warnings or disqualification at the discretion of the organization. So, don't you dare violate any of our hackathon rules and guidelines. The top 10 teams will present their projects to the jury during the final session. Teams should be prepared to demonstrate their solution and answer the jury's questions very clearly and crisply. Winners will be announced at the closing ceremony. All decisions made by the jury regarding awards and rankings are final and binding. Teams are encouraged to continue refining and developing their ideas beyond the hackathons also. It will be very much useful to you, to the institutions, and to the nation also. Participants are encouraged to provide feedback on the event to help organizers improve our future hackathons and events, any potential occurrence which might occur. Sharing learning, challenges faced, and solutions implemented is a highly encouraged. And for any queries or clarifications, or if you are needing any assistance before or during or at the hackathons, participants can reach out to the organizing team. The email and WhatsApp mobile numbers or our website, which is quantum.rgukt.in. You can access or you can contact us for help through all these means. We are really excited to welcome you to the Qiskit Fall Fest 2025 Hackathon. This is really an opportunity to innovate, collaborate, and showcase your skills in quantum technologies. We encourage all the participants to stay creative, respectful, and focused, making the most of this 48-hour long hackathon and challenge. We wish you all the very best and look forward to seeing your innovative ideas come to life. I hope you're all a bit clear about the hackathon guidelines now. If any of the hackathon guidelines are improvised or added or modified, we will be letting you know when you reach the venue for the hackathon. And for now, that's all about our hackathon guidelines. And that's all, guys. And following this, we'll be having the workshop session within a few minutes. Thank you. The first session of today's day 5 of Qiskit Fall Fest 2025 is a hit, absolutely. And as we move forward with the day, we are all set to continue our learning journey under the guidance of someone who's been making quantum computing feel both fascinating and approachable also. So, in this session, Dr. Gnan Yala sir will continue leading us through the core ideas of quantum computing, helping us gain a deeper and clear understanding of how quantum principles are shaping the next generation of computation and innovation. So, let's keep our minds open for lots of knowledge coming our way, our spirits high, and our curiosity alive as we dive right into this session. So, ladies and gentlemen, please join your hands and join me in giving a huge round of applause to warmly welcome Dr. Gnan Yala sir as we begin the day 5 workshop session of Qiskit Fall Fest 2025.
Okay. Hello. Okay. So yes, good morning everyone. So today is Saturday, right? So kinda informal in nature, but yeah, completely all right. Because the thing which matters is the thing what I'm talking, right? It's not the way how I'm dressed. Okay, it's a good one, but still. Okay, cool. So today will be the last session of our workshop kind of thingy. So where I would like to explain about this entanglement in nature, which I have been talking about in the previous session. So in a previous session, I completed or I start with something called as entanglement. So from there, I will just carry on the session, like what is entanglement and how our belt states are classified and what is a belt state first of all and all those things. Cool. So yeah, let's directly start. Why? Because I have very low time today, I guess, up to 12. So that's why I'll just start the stuff. And let's see up to where I'm able to cover it. And then from there, I will give you the resources. Okay, you guys have been asking me about the resources since the first day. And the reason why I did not give or I did not say about the resources is that I don't know where we will complete, right? And from the point we complete, from there, what you can do another, I will provide you the resources accordingly. Cool? So, yes. First is entanglement. So, first of all, what is entanglement? What did you understand by entanglement? What is this? Correct only, but what is that exactly? Two of the qubits. Let us consider two qubits. Let us consider, but it's technically more than one qubit. More than one qubit, what will happen to that? They will be heavily correlated. Two qubits are heavily correlated in such a way that what will happen? Simply to put, the measurement of one qubit will directly influence the measurement of another qubit. Okay, so two qubits are heavily correlated in such a way that the measurement of one qubit, let us consider two qubits A and B, are heavily correlated in nature. So when these two qubits are heavily correlated in nature, what will happen is that if a qubit A is measured, when a qubit A is measured, it gives a significant output, right? So when qubit A is measured, this eventually influences the measurement of qubit B. The measurement of B will be influenced with this measurement. So that is your entanglement. Simply to put, that is the entire meaning behind your entanglement. The measurement of qubit A will directly influence the measurement of qubit B. So that is known as entanglement in nature. Got it? Now, what is the meaning behind this measurement influencing the measurement and stuff like that? Or what is the entire meaning behind this influence the measurement? Very simple. So, what do I mean when I say influence the measurement is that if a qubit A, when measured, gives a particular output, through this output, we can define or we can find the output given by qubit B. So that is the entire deal behind it. So we don't need to measure qubit B explicitly. Explicitly, we don't need to perform the measurement on qubit B. By simply measuring the qubit A, we'll get a single value, right? And by having that value and by considering that value, we can find the measure the output of qubit B. So that is entanglement, and that is the meaning behind this influencing the measurement and stuff like that. That's a simple deal. Now, so there are some entanglement states through which we can say like if it is 0, this is also the 0, or if it is 0, this can be 1 or stuff like that. Okay. So yeah, I've just explained it in a very clear way. Right? Simple. So technically, there are only two possibilities. So there are technically four entanglement states. So which we will call it as bell states, which I will explain right now, like the bell states and stuff. So there are totally four entanglement states, which we will call it as bell states as well. Okay. Now, these four entanglement states gives rise to or breaks down into two possibilities. First possibility is that two qubits A and B. If a qubit measurement is 0, then the other qubit measurement is also 0. Okay. This is one possibility. This is one possibility of your entanglement state. The second possibility is what? If it is 0, this is 1. That is the second possibility of the entanglement states. Okay. So first possibility, what will happen? If my qubit I measured gives an output as 0, then the entangled qubit will also give me the same answer. Okay, that is the first possible case of entanglement. And second possible case of entanglement is that if a single measurement came out to be 0, then the other qubit measurement will be the opposite. So that is the second possible condition of our entanglement states. And as I said, there are totally four entanglement states annan kada. This possibility is given by two states and this possibility is given by two states. Okay. So why two states ante? One state is plus and one state is minus. That's a simple deal. Meaning, what is the meaning behind plus and minus in case of quantum? Is it the value or what is it? In yesterday's session, I have explained. It is the direction. What do you mean by direction exactly? It is something called as that word is important. What is that word? Phase. Very good. It is the phase of the value. Okay. It is not the actual value. Actual value is this thing only. If it is 0, this is 0. That is one possible case. And that possible case can be given by two of the entanglement states. Out of four, two entanglement states gives me this possibility. Why two ante? Simple. Out of these two, first thing gives me the same phase and the same value. And the second thing gives me the opposite phase, meaning the opposite angle. But the same value, but with the opposite angle. That's the only thing. Same goes for the opposite stuff as well. Okay, I will explain this very clearly. But this is how the entanglement state behave. And this is how the measurement influences. Okay, now? So that is the entire deal behind it. Now I will explain about bell states. And then in yesterday's session, I also told about one point. What is the one point I told? Entanglement states breaks two properties of physics. What are those two properties? Locality and realism. So, how scientists found that they are breaking the locality and realism? Why it is important is, for example, no one went to Andromeda galaxy to actually test that. right? And no one did any stuff because the humans are there in a perimeter where the light traveling is so fast that the distances or the difference in time cannot be measured yet. Okay, so that's why there is no possible way in order to find the locality. So I can't possibly say that it breaks the locality. So, but how did the scientists actually found that the entanglement is breaking the locality? Are you guys getting the point? So technically, by doing some experimentation or stuff, I can't say that it's breaking the locality. Why? Because the humans are in a perimeter or humans are in the area or a range where the small differences in the distance will not alter the speed of light. So if I am here and there is some person here only, and if I talk to him, definitely the speed is the speed of the light through which the information is going, something lower than the speed of the light, but approximately equal. But the same person, if I call it in the phone who's in US, he will also seem to be receiving the answer in the same time, but there will definitely be a difference. But the difference is very small that it can be negligible. So approximately the both will be kind of equal only. So that's why there is no possible perimeter or there no possible scope where I can actually do the experimentation to find localities being broken. Are you guys getting the point? So if I have the ability to go to Andromeda galaxy, and then I can say experimentally that locality is being broken, bro, and ship. But at this point of time, I can't. So what is the experiment the scientists did in order to find the localities being broken? So that's one also we're gonna see actually. But before actually seeing that, we need to know about Bell states. Bell states. So how many Bell states are there? Just now I explained. How many are there? 4. So these 4 Bell states can be called as phi plus, phi minus, psi plus, and psi minus. Okay. So these are real values. They are not variables. ఏదో ఒకటి పెట్టుకోండి కాదు. We should definitely keep this thing only. So why? Because in yesterday's session I have mentioned something known as plus state, right? So this plus state is what? What is this plus state? చెప్పండి. 0 plus 1 by root 2. This is the plus state. And what is the minus state? 0 minus 1 by root 2. That is the minus state. How I can get my plus state? Correct. What is that? Hadamard gate with ket 0 gives me this one. And Hadamard gate with ket 1 gives me minus state. Okay? Cool. Now, Bell states are also like that they are properly defined states anamata. It's not like just like that, properly defined states. So this guy 5 plus is the 0 0 plus 1 1 by root 2. And 5 minus is 0 0 minus 1 1 by root 2. This is 0 1 plus 1 0 by root 2. And this guy is 0 1 minus 1 0 by root 2. Okay. So these are the 4 Bell states. 5 plus, 5 minus, psi plus, and psi minus. Now I will ask you one question. What are the Bell states which is responsible to define whether A's qubit is 0, then B's qubit is also 0. So in which entangled state can I say like this? Can you guys get the idea of it? I mentioned you one thing about entanglement. If I measure one qubit, that measurement will influence the second qubit and thereby giving the output of the second qubit and shift RAM, right? And I also told there are 2 possible cases. One case is where both answers are equal. Second case is where both answers are opposite. So if I take the equal condition, which entanglement pairs or which entanglement state is responsible for giving this equal output? 5 plus 5 minus psi plus psi minus. Out of these 4, which entangled states are responsible for giving the same output? 5 plus and 5 minus. How you can guess that? Simply look at this thing. You can easily understand that. Okay. So here we are having same notations. Sarana? So that's the basic deal behind it. So this is the simple deal. So by just looking at that, you can understand what is the possible answer is. And you can directly do the stuff. Okay now? Now, what exactly is not and 1 1? Asal 0 0 1 1 ante ఏంటి? Before, why? Because before we have seen only 0 and 1. Kada? We have seen about 0. What is 0? What is 0? Cat 0 value inte 1 0. Yes. Cat 1 is 0 1. Okay. But what is this new guy? Now, let's give rise to, I hope you guys have copied this one. So let's give rise to one new thing actually, which is known as a tensor product. Picture light very easy. That's very easy. It's not very different or something. Very easy, straightforward it is actually. And this tensor product is a linear combination of gates or matrices. Okay, tensor product is a linear combination of gates or matrices. For example, if I'm implementing 3 gates sequentially, if I'm implementing gate A, gate B, and gate C on 0 get, meaning is this guy can be written as this on I can write in this way anamata. And this symbol is known as tensor product. Okay, keep a circle, keep an X inside a circle. Okay, tensor product. So multiple, the linear combination of matrices, meaning the linear combination of gates can be written in the form of a tensor product. Okay, now these states can also be written in the form of a tensor product. The combination of states can be written in the form of a tensor product, meaning ket 0 tensor product of ket 0 give rise to ket 0 0. Okay na? So when I write that 0 0, ket 0 0 and rasnapudu, the meaning behind that is this one. Ket 0 tensor product of ket 0. That gives me rise to 0 0. Then what is this? Ket 1 0 ante enti? Ket 1 tensor product of ket 0. Okay? This is not commutative in nature. Keep that in mind. This is not commutative. What do you mean by not commutative? A tensor product of B is not equal to B tensor product of A. So please keep that in mind. That's why when I say ket 1 0, it is only ket 1 tensor product of ket 0, but not ket 0 tensor product of ket 1. Both are different. Okay, na? Now, how I can find this one? Okay, I talked about tensor product, but how I can find a tensor product? Very simple. What is 0 vector? Ket 0, 1 0, right? So when I say tensor product, it is nothing but, for example, if I go 0 0, is nothing but ket 0 tensor of ket 0, which is nothing but 1 0 tensor of 1 0. Okay, so it's something like this. What is this? How to do this? Really, people will say a lot of different methods, but the easiest way, direct, that easy way is this one. First matrix is there, na? Okay. Second is there, na? This over answer. So this is your tensor product. Okay. This into the entire matrix, the second value into the entire matrix. That's it. Tensor product is done. So what is the output? Right? 1 into 1 0. What it gives? It gives 1 0 only. 0 into 1 0. It gives 0 0 only. Got it? That's all. Tensor product is over. Adavainda, this is a simple way in how you can do an tensor product. Direct approach. You don't need to do the entire thing. Simply there will be 2 matrices, right? Each element into the complete matrix. Each element into the complete second matrix gives rise to the tensor product. That's it. Very easy and very straightforward. Okay, na? Everyone. Done? Understood this one clearly? Cool. Now in a similar way, I can do all the stuff. So when I say 0, 0, it is nothing but what? 1, 1, 2, 3. When I say 1, 0, it will be, try to do that. So 1, 0 gives like this. It will be in this format. So when I say 0, 1, it will be in which format? And when I say 1, 1, it will be in 0, 0, 1, 0, 1. Okay, I don't believe you. Thank God I did not believe you. Okay, so this is how the states look like. Okay, now? So this is the this is not entanglement state. These are nothing but called as 2-qubit states. These are called as 2-qubit states. And the entanglement pairs can be achieved by using the 2-qubit states. So why? Because we are working with 2 qubits, but not a single qubit. The single qubit states are 0, ket 0, ket 1. They are single qubit states. But as I'm working with 2 qubits, they come under my 2-qubit states. Okay, now? Understood? Simple, straightforward stuff. Now, first step of entanglement. So now you are clear with the belt states. So if anyone asks you belt states, these are the belt states. Phi plus phi minus, psi plus psi minus. They are known as belt state. Now, how I can prepare the belt states? So how I can prepare belt states is directly equal to how I can create my entanglement states. So if anyone asks you to create a superposition state, what you will do? Use a Hadamard gate. So if you use a Hadamard gate, you can create a superposition state. If anyone asks you to create an entanglement state, they will come and they will be like, bro, I need to create an entanglement state. How? At the time, how you can do that? And very simple. First, let me create 2 qubits. Okay. And create a superposition of first qubit. Creating a superposition of my first qubit. If I apply a Hadamard gate, I'll create a superposition of the first qubit, thereby making it in a superposition state. Now, right now, it's in this particular state. And this guy is still in my 0th state. Now, if you apply a C0 gate, now if you clearly apply a C0 gate, this thing will become a 2-qubit state. Okay. So as it becomes a 2-qubit state, this gives rise to something called as a phi plus state. Okay. If anyone asks you to develop a entangled state, the first step is to use a Hadamard gate. When you use a Hadamard gate in the first qubit and a Q naught, and the qubit starts from 0. So that's why the first qubit is Q naught, second qubit is Q1. Okay. So first make the Q naught, make the first qubit go into a superposition state. And after the first qubit goes into a superposition state, keep a C naught by keeping that superposition state as a control and this guy in the this one. Okay. And try to do this particular thing. You will get the output as a phi plus state. So what do you mean by phi plus state? Simple. This is what 0, 0 plus 1, 1 by root 2. Right? Now, what do you mean by 0, 0 plus 1, 1 by root 2? So what is 0, 0? So what is 0, 0 state? How does 0, 0 state look like? 1, 0, 0, 0. Okay. This is the 0, 0 state, which we've seen before. And what is the 1, 1 state? How the 1, 1 state looks like? 3 zeros followed by a 1. 0, 0, 0, 1. So, 5 plus is nothing but 1 by root 2 of 1, 0, 0, 1. Okay. So meaning very simple. This is the 5 plus state I have mentioned. Yes or no? What did I do? I simply expanded the guys. That's it. Meaning get 0, 0, I defined it in a column format. And get 1, 1, I defined it in a column format. And then I simply did the addition. Obviously, they both are the addition, right? And we got this particular thing. So this is your 5 plus state. Your 5 plus state will look something like this 1 by root of 1, 0, 0. Okay. So that is how your 5 plus state looks like. Sarana, a simple case. Now, how we can actually achieve this one by doing this? So how we can actually achieve by doing this? Very simple. From 0, 0, try to apply each of the case. You will get the answer obviously. Okay. So by just doing a continuous matrix multiplications and stuff, you can easily observe the final answer directly. Got it? So that's how this stuff works. And that's how you can create a something known as a 5 plus state. Now, okay, bro, I created a 5 plus state. Now, if I want to create a 5 minus state, I want to create a psi plus state. I want to create psi minus state. How? So the first entanglement state, which we eventually create or which we always create, is something called as a 5 plus state. So we created a 5 plus state by using a header mat as well as a single C naught. I use one header mat and a single C naught. I created a 5 plus. Very good. How I can create a 5 minus, psi plus and psi minus? Very simple, very straightforward. The first step is to create a 5 plus state always. Always create a 5 plus state. So I use a header mat and I use a C naught. I created a 5 plus state. Okay. After I create a 5 plus state, if I want to create a 5 minus state, what I can do? In the second qubit, try to apply a Z gate. If you apply a Z gate on the second qubit, the phase will flip for only which phase? I mean, for which state the phase flip will happen for Z gate? One state. Okay. Right now, what will happen up to here? It is like this. Okay. When I'm using Z gate, what will happen? The phase of first state will flip. So after this, the output will look like 0, 0 will not change. It will not affect. But only one state's phase will be flipped, right? So one state phase is flipped. Got it? What is this? 5 minus. Okay, now? So this is how this thing works actually. So if you want to create a 5 minus, very simple, just keep a Z gate. Just keep a Z gate on the second qubit. It will create a 5 minus. Now, I want to apply this one. I want to apply psi plus. So how I can apply psi plus? So I don't want to draw the circuit, so I will directly do it. So 5 plus is nothing but which C naught on HI for my Q naught. అని వేసుకుంటాం. Q naught అంటే first cube, obviously. And 5 minus is nothing but Z on my 5 plus. ఇది చెప్తాను ఇంకా క్లియర్గా ఏంటి ఇది అని చెప్పి. And your psi plus is nothing but X with my 5 plus. And a psi minus is nothing but Y with my 5 plus. Now, here I used tensor product of I. But here I did not use anything. Why? Very simple, very straightforward, very easy. ఏంటంటే if I want to apply the gate to my first qubit, ఇక second qubit నేను ఏమైనా అప్లై చేశానా? Is the second qubit is having any type of operation in this point of time? No. That's why I will make it something like this. Why? It is a 2 qubit state. So as it is a 2 qubit state, we require 4, 2 qubits కాబట్టి we require 4 states, meaning we require 4 cross 4 matrix, but not 2 cross 2 matrix. But my H is what? H is a 2 cross 2 matrix. But I am applying a H for what? For 2 qubits, meaning for 4 states. Upon nena 2 cross 2 matrix me, I will convert that into a 4 cross 4. So how I can do that? By simply keep an identity for my second matrix. So the meaning entante this one. If I apply identity, will there be any change? Q not. Identity apply చేశాను ఏమైనా అవుతుందా దాని state కి nothing will happen, it will be still be the same. So that is the operation what I'm doing. So when I say H tensor of I, the meaning is for the first qubit apply a Hadamard, second qubit there's no change, just like that it's staying. Okay, this is a mathematical notation, this is how we need to show it off mathematically. And here I did not use anything. Why? Tensor of I and M వాడలేదు. Why? If you want, I can go like this actually. ఇలా వేస్తాం ఇంకా వేస్తే. So we can go like I tensor of Z, I tensor of X, and I tensor of Y. What is the meaning behind it? Meaning is first qubit mein there is no change. I don't want to apply anything to my first qubit. So first qubit is identity. Second qubit mein I want to apply the Z gate, X gate, Y gate and చెప్పాలి. Got it? This is a simple case. Very straightforward definition. When we are dealing with a 2 qubit state, we want totally 4 output states. As we require 4 output states, we require 4 cross 4 matrix. But the Z gate, X gate, Y gate, H gate all are 2 cross 2 matrices, which we cannot apply on a 4 cross 4 thingy. So for that reason, we simply make it identity. Identity tensor of Z is student. You'll get a 4 cross 4 matrix. Okay, why? Because I'm applying it on 2 qubits. Got it? Got the logic? Simple case. This I defines the qubit through which we are not applying any change. H tensor of I, meaning apply H on first qubit. There is no change in second qubit. Ani adda. So I also mentioned 5 minus is achieved by keeping a Z gate and the second qubit. Kada? That's why I went I tensor of Z. When I go with I tensor of Z, the meaning is no change in the first qubit. First qubit atlane unchu. Second qubit may keep the Z gate. Keep the Z gate in the second qubit. Then it will do the 5 minus. Now, what is the meaning behind this actually? చెప్పరా గట్టిగా. Exactly. So what we are actually doing here, first we create a 5 plus state by using a Hadamard and a C naught. I'll use a Hadamard gate, I'll use a C naught gate, I'll create a 5 plus state. After creating a 5 plus state, what I am doing? Use an x-axis x gate for my which qubit? Second qubit. Got it? So that's the thing which we are doing here. Use an x gate to my second qubit. Thereby it will convert it into a psi plus state. Okay? Now, to get a psi minus state, what is the deal? Create a 5 plus state. So this is the 5 plus state. Create a 5 plus state. After creating a 5 plus state, what you need to do to get psi minus? By looking at this, can you say? Second qubit mein apply the Y gate. If you apply the Y gate in my second qubit, you'll get a psi minus state. Got it? Simple deal. Just by looking at the notation, you can understand what is happening. Okay, now? Now. So this is how you can prepare a and belt states or called as an entanglement states. So these are known as maximally entangled state actually. I'm meaning they are heavily entangled in nature. Normally entangled antene heavy relation. But when I say maximally entangled, the meaning goes like they are very heavily entangled in nature and these are the belt states. Dini mano maximally entangled states ankoda antamu, we will call them as belt states as well. Got it? So that's the difference. Now, Now let's go to the experiment actually. So I mentioned you that entanglement states might they are termed to be breaking the locality and realism and shape approximate. How did the scientists find out? So there is something called as a Bell measurement, or not Bell measurement, sorry, it's inequality. Bell inequality. So there is something called as a Bell's inequality where the scientist called Bell, I don't remember his first name, I think John or something. So he created a series of tests where he had a lot of inequality methods, out of which the famous one is known as CHSS inequality. What is the meaning behind this CHSH inequality? Ante very simple limit. Limit goes like this. For example, if I take two states, A and B, whose outputs can be +1 and -1. And they can be +1, they can be -1. They are the possible outputs, like true or false, like an unknown. Okay, but they are not 0 and 1, but instead +1 and -1. Same, B can also be +1 or -1 accordingly. Okay, so these are the cases, these are the possible answers. A can be +1 or -1, B can be +1 or -1. Now, at any point, really, classically, or normally, if you calculate perfectly, yes, A dash, B dash should be 2. Okay, this is the limit actually. Okay, so what is this? And nothing but a simple thing. Now, asal idi enti ante, which I will just explain this one as first, right? This is a limit actually. So really, this limit should not be broken. If this satisfies locality and realism, if locality and realism are satisfied, ఒకవేళ రెండు correct, ఆ రెండు satisfy అవుతే, it should satisfy this equation. If these two are preserved, this equation or this inequality should be satisfied. Meaning, if I calculate this entire value, it should be lower than or equal to 2. It is rule. Okay, pakka rule. Okay, that's a rule. If locality and realism is preserved, if these two things are preserved, then this is the rule behind it. Okay, definitely it should be like this. Now, what is this value? And to be honest, so if I take AB, this is nothing but probability of A equal to 1, B equal to 1, plus probability of A equal to -1, B equal to -1, minus probability of A equal to -1, B equal to 1, plus, sorry, minus probability of A equal to 1, B equal to -1. ఇదన్నమాట AB కి మీనింగ్. ఓకే, సింపుల్ AB. సో AB కి మీనింగ్ ఏంటంటే ఇది. So this is the probability which you guys know already. So probability of A equal to 1 and B equal to 1 value is it. So these are the respective values. And this is the A inner product. Clearly it's not an inner product, but that's the notation which they use at this point. So this is the meaning behind this. Okay. Now, if this is satisfied, the meaning goes like locality and realism is preserved. How it is only 2 ante, it's a very big meaning behind it. So we don't need to go to very clean mathematics or very clean QM or something like that. But just remember this is the inequality. The inequality is this one. So if I calculate all these values, yeah. So if I calculate all these values, it should be lower than or equal to 2. And where each value is this. It looks like this. Okay. So A, B అని తీసుకుంటే this is the meaning behind it. సరేనా? డాష్ అంటే ఏంటి? కాంప్లిమెంట్. కరెక్ట్. 1 మైనస్ చేసుకోండి అయిపోద్ది. Okay. Now, but when the bell guy he did the measurement by using quantum states rather than your classical states. And a quantum state, in a sense, he did an experiment actually by using the particles. So which we don't need to go deeper about it. But nothing but a quantum state unquote, simply to put. When he did the experiment with the quantum state, he got the output as this one. Okay, which is greater than the 2, obviously. Okay, but the limit is what? The limit is it should definitely be lower than or equal to 2, right? So if I calculate this value, the output should definitely be lower than or equal to 2. If it is lower than or equal to 2, then these qualities are preserved and it is following these qualities ani artham. Okay, but when Bell experimented and he found the value of this particular thing by using A as a quantum state and B as a quantum state. A ni B ni quantum state can use చేసి try చేసినప్పుడు he got a value as root 2, 2 root 2, which is eventually greater than 2. Thereby saying that, bro, these two are not preserved, bro, and simply to. Meaning this is only not preserved. Obviously, conflict వచ్చేస్తుంది. So not. So thereby through this he understood that no, it is not preserving locality for sure. Okay, and thereby your entanglement will not satisfy locality and helps in the Dhinvan. This is the simple thing. Got it? Don't go into deep mathematics like how it is 2, how he got 2 root 2 and all. I was not later at this point of time. Until or unless you want to be an optical scientist or something, you don't require those things at all. Or if you want to go to quantum communications, you don't require these things at all. At this point of time, as a beginner level, at this point of time, you don't require the deep mathematics of it. But this is the entire deal. This is how they found out that this is possible. This is breaking the locality and chip. Advainda, this is known as Bell's inequality. This thing is done, na? Bell's inequality. Okay, Bell's inequality means there are a lot of things. In Bell's inequality, this is specifically known as CHSH inequality. Okay, Bell's inequality means you have something like 2 to 3 types are there. Out of those 2 to 3 types, this is just one of the experiment which is known as CHSH inequality. Okay, a simple deal behind it. Done? Now. Now let's actually go to two of the use cases which we can directly do it by using this entanglement concept. By using this entanglement concept, we can do two of the cases actually. So where my first case is called as super dense coding, and the second thing is called as quantum teleportation. Okay, so there are these two things which we can actually do by using this concept of entanglement in nature. Okay, now first let's start with the super dense coding. Like, what do you mean by this super dense coding? Very clear, very straightforward, very easy. Okay, chala easy super dense coding. And there's not even a single concept behind it. First, let's see the problem. Like, what is the problem and what super dense coding actually satisfies? Simple. First thing, let us say I want to send you 2 bits of information. Okay, 0 1 no 1 0 1 1 no 0 0. Out of these, for any one thing, I want to send you. I want to send you 2 bits of information. How many classical bits do I require if I want to send you 2 bits of information? We require 2 bits. So each bit carrying one information, right? So 1 bit carries only one information. So 1 bit carries either 0 or it carries 1. So for transforming or for transferring 2 bits of information, I require 2 bits, 2 classical bits. So 0 1 1 0 1 1 0 0. So these 4 low, any one of the information which I wanna send you. For that I require 2 bits. Okay. I require classical, I require 2 CL bits. CL bits ante ente? Classical bits. Now, but by using the super dense coding, concept, and which uses the entanglement properties of stuff, we can send these bits of information by just using a single qubit. Okay, we can send a 2 bits of information by using a single qubit. How, why, we will see. Okay, simply by using the concept of entanglement in nature. By just using the entanglement in nature concept, we can do this particular stuff. How we can do it? Simple. First thing. So what is the entire concept of this, Ante? There are totally 2 qubits in the game. So in the entire superdense coding system, we will be having 2 qubits. Okay, we will be having 2 qubits. And these 2 qubits are, 1 qubit is given to Alice and 1 qubit is given to Bob. Okay, so Alice and Bob are 2 people. If you want to give, you can give your own names, not a problem. Keep A and B, Raja Rani, ఏదో ఒకటి పెట్టుకోండి, ప్రశ్నే ಇಲ್ಲ. Okay, but theoretically it is Alice and Bob. Okay, so 2 qubits are there in my system, which are heavily entangled, meaning I am entangling them in this state. What is the meaning behind this? Which state this gives rise to? 5 plus. Good. This gives rise to 5 plus state. What is the 5 plus state? It is one of the belt state is 0, 0 plus 1, 1 by root 2, which is known as maximally entangled state. If I tell you to create a entanglement state, what you will be doing? First, apply this thing. You will create a first entangled state, simply, over. Okay? So, I entangle 2 qubits and I will send 1 qubit to Alice and 1 qubit to Bob. Okay? Now, the transfer is, Alice should send these 2 bits of information to Bob. Okay, na? Alice should send 2 bits of information to Bob. Okay, now comes the deal here. This is the real one. Okay, it's not just like that. The real thing. Ide cheyali rule. Now 2 qubits are entangled in nature, right? So 2 qubits are entangled. And Alice has Q0 and Bob has Q1. Now, based on the 4 of the states, 4 states ఉన్నాయి కదా, అంటే 4 states కదా 4 types of messages ఉన్నాయి, out of which any one thing is being sent by Alice to Bob kada. 2 classical bits of information, that there are 4 possibilities, out of which one thing. If Alice wanna send 0 0 to Bob, okay, Alice 0 0 అనే స్టేట్ అంటే 0 0 మెసేజ్ ని బాబుకి పంపాలనుకున్నాడు అనుకుంటే, he need to apply any gate. అతను ఏ గేట్ అప్లై చేయాల్సిన అవసరం లేదు. ఓకే, సో దిస్ ఇస్ దిస్ వన్. వాట్ ఈస్ ద మీనింగ్ బిహైండ్ దిస్? కరెక్ట్. Q0 I, Q1 is also I. ఏం చేంజ్ లేదు అక్కడ, పిచ్ లైట్. ఇఫ్ Alice wanna send 0 1 to Bob, bro, I need to send 0 1 message to Bob. I don't wanna send 0 0 classical bit ని పంపాలనుకోవట్లే. I wanna send 0 1 message. If Alice wanna send 0 1 message to Bob, he needs to apply, he or she or ఏదో ఒకటి, she needs to apply X gate. Okay, meaning Q0 లో నేను X gate ని అప్లై చేయాలి. Got it? So the meaning behind this is what? X is applied to Q0 and I is applied to Q1 అని అర్థం. Okay na? This is the meaning behind it. Just keep that in your mind. So if I go like A tensor product, కనిపిస్తుందా? Yeah, okay. If I go like A tensor product of B, the meaning is A is being applied to first qubit and B is applied to second qubit. Okay? If Alice wanna send 0 1 message, now if Alice wanna send 1 0 message నేను పంపాలనుకుంటున్నాం బ్రో అంటే, she should use Z gate. Okay, if Alice wanna send 1 0 message to Bob, she should use Z gate. And at the last case, if she wanna send 1 1, she should use Y. Okay, so these are the things which should be applied by Alice to the qubits when we want to send any type of message. Okay, na? The entire case is what? Alice want to send 2 bits of message to Bob. Okay, and the 2 bits of message can be 00, it can be 01, it can be 10, and it can be 11 as well. So based on the message which she want to send to Bob, she will apply the gates. Okay, if she want to send 10, she will apply Z gate. If she want to send 11, she will apply Y gate. Alaganmat. Okay, based on the type of message she want to send to Bob, she will apply the gate. Okay, first obviously we will be creating this thing, that is for sure, because they are entangled in nature kada. So first we will create an entanglement thing, entanglement state create chestam, 5 plus vachestade, and then we will apply these things. Got it? Now let us consider she want to send 10. Alice want to send a message called as 10 to Bob. Now what will happen? Which gate she should apply? She should apply Z gate. To which qubit? Q0 or Q1 na? Q0. Good. Here I will apply Z. Okay, that's it. Sorry, that's it. Done. Now the states is being encoded into an entangled point. Now this thing will be sent classically to Bob. Okay, now ఇక్కడ మీకు ఏమవుతారంటే classical simulation అవుతుంది. So I will just keep like this and I will write it like classical simulation. Okay, I will just create a new circuit. So let's just wait a minute. Say Q0, Q1. First I will create a what? Entangled state. And after creating an entangled, so this is an entangled state. So 5 plus, and then let us consider the message is 10. So here it will create a Z gate and the 10 is being sent. Now here I am considering a classical simulation. So what is the meaning of this classical simulation ante? This is entire state is there na? This entire state that will be sent to Bob through classical channel only. Quantum channel అవ్వాల్సిన అవసరం లేదు. నేను classical గా పంపిస్తాను state ని, which this complete state up to here, from here to here, I'll be sending it to Bob classically. Classically I sent to Bob. Let us consider I sent to Bob. B కి పంపించేసాను. Now what will Bob do? Bob will do something called as bell measurement అంటాం దాన్ని. Bob will perform something called as bell measurement. So what is known as bell measurement ante? Reverse the 5 plus entanglement. That will be bell measurement. How you are going to get 5 plus? 5 plus ఎలా achieve చేసాం? Here in the circuit. You applied a Hadamard gate and you applied a C0 gate. Kada? Bell measurement is a reverse operation of 5 plus gate. Meaning what you will be doing? First you will apply what? C0. First we will apply C0 gate. First I will apply C0 gate. And then what I will apply? I will apply a Hadamard. Sorry, circulation. That's it. So this particular concept where I'm applying the reverse 5 plus gate is known as my bell measurement. Okay, I will do this and I will simply measure it off. I will get the, what can I say? I will get the answer. Now I will do measure all. Actually, now after doing this, what I will be doing? I will be doing performing my measurement. So what is a measurement? So what is this signifies? This signifies the presence of classical bits. Now what I will do is simply perform the measurement. Got it? So this is how I will create my super dense coding circuit in order to send which information, which classical bit is being sent by Alice to Bob in this circuit. Correct. 10. So this information of 10 is being sent to Bob from Alice. And this is the circuit for that. Okay. First, create an entangled state. Okay. First case when an entangled state will be created. And after an entangled state is created, based on the information Alice wanna send to Bob, she will apply the gate. If she wanna if she wanna send 10, she applies Z gate to Q naught. Okay. And then this prepared state she will send in the with the true classical something to Bob. And after this state is being received by Bob, what will happen? He will apply something called as a bell measurement. Bell measurement is the reverse of your 5 plus state preparation. Okay. And it is a C naught followed by a Hadamard because 5 plus anti Hadamard followed by a C naught. Reverse C naught. And after doing the bell measurements, he will simply measure them all. That's it. He will measure Q naught, he will measure Q1. Q naught of a measurement is 0 calteri, Q1 of a measurement 1 calteri. IPN. Now if you see the output, now the output will be in a probability of the states where 1, 0, right? It will look something like this in the graph. Graph may it will look something like this. So this will be here, and let us consider this here. This will be here, and this can be here. So this is how the output and probabilities look like. And this is state. So this is how it looks like. So where the 1, 0 is having, oh sorry. So I'm sending 1, 0, right? So it will be like this. Yeah. So if I'm sending 1, 0, I'm sending the information of 1, 0. Okay. As I'm sending 1, 0, this guy will show heavy probability. Why? So what I'm sending a classical bit of 1, 0 kada. Nen pampedi 1, 0. But if you perform this circuit and if you visualize the output, the output will look something like this. Why I'm sending 1, 0, right? Why 0, 1 has heavy probability? 1, 0 should have heavy probability, right? Why? Because simple. Answer is 1, 0 only. But when doing this thing, what will happen ante? It will take the values in this way, Anuman. Okay, so it is not 0, 1. It is 1, 0 only. Idi 0, 0. It is 1, 0. This is 0, 1. Idi 0, 1. Idi 1, 1. So why? Because it will read in the reverse order when you are actually finding the probabilities. Sarena? So this is your super dense coding. Okay. So yes, I think the time is already up for me. I am running 2 minutes late. So yeah, I guess I will just conclude my session till today. So till here. So yeah, thank you for giving me this opportunity. Thank you.
Thank you so much, sir, for the truly enlightening and thought provoking workshop. The entire workshop is for sure a damn hit on quantum algorithms and hybrid machine learning. It was such a perfect way to set the tone for any days in the Qiskit Fall Fest. And what do you say, guys? I would like to say Dr. Gnan sir undoubtedly deserves a humongous round of applause for all his efforts, the time he have taken for us, and the patience and generosity he showed. This is by far the best workshop experience for all our attendees, sir. Really, thanks a lot. Now, as we continue our journey, our learning journey through the fascinating realm of quantum technologies, it's time to move into yet another immersive guest lecture initially and hands-on session, the one that brings abstract world of qubits and circuits right to our fingertips. And it's my absolute pleasure to introduce Mr. Tilok Sadhu Khan, quantum computing engineer and quantum algorithms developer at the Center for Development of Advanced Computing, CDAC, Bangalore. Mr. Tilok sir is a passionate researcher and educator who specializes in quantum algorithm design, simulation, and implementation, working tirelessly to integrate quantum computation into both practical and educational frameworks. He has been an active contributor and helping shape initiatives that promote quantum education and hands on learning across India. At CDAC, he contributes to the algorithmic research and simulation frameworks, and is best known for his work on Quniverse, a platform designed to make quantum learning more accessible and application oriented. Beyond his technical brilliance, Sir is deeply committed to nurturing India's quantum ecosystem, mentoring young minds, learners, guiding researchers, and inspiring the next generation of quantum innovators. And today he'll be leading us through an exciting guest lecture initially, followed by a hands on workshop on Quniverse, where we will experience the practical side of quantum programming, experimentation, and innovation. So let's keep our curiosity alive and our enthusiasm high. Please join me in giving a warm, energetic round of applause to Mr. Tilok Sadhu Khan. And now I wholeheartedly hand over the dais to him to take on this wonderful universe experience.
So it's actually Linux. Hello, hello. Am I audible? Yeah. So, hello everyone. I'm Tilak. So actually, I'm from CDAC Bangalore Quantum Technology Group, and today I'll be mostly speaking about. Today I'll be delivering my talk in primarily two segments. The one is first I'll describe a platform called Quniverse, what it is, what it's good for, what kind of things you can do with it as a students, young researchers like all of you. And secondly, I'll showcase an algorithm, specifically the time evaluation of a quantum system, which I actually implemented that algorithm into the platform in Quniverse itself. So these will be the two segments of my talk. In the second session, I'll be giving the algorithm demonstration that are based on the trotterization. In the first segment, I'll be giving the talk on hands-on demonstration on Quniverse. So, so, so just to begin with, how many of you are just a beginners in quantum computing? Raise your hands. Okay, a lot of them. Okay. Now I'm actually very worried about should I really discuss about trotterization based on those algorithms because it's a bit tricky. But if you stay a bit patient, you will maybe have a much more intuitive understanding. Okay. No, but still, I'll try my best to explain things in as simple as possible so that all of you have a really good understanding and get benefited from this platform. Yeah. So, as I said, most of you are just a beginners and probably does not have a really good understanding about quantum mechanics or quantum computing. So, I think so. I can start off this talk with this famous quote from Richard Feynman, which is a famous physicist. I think all of you have heard about him. So he said something like, I think I can safely say that nobody really understands quantum mechanics. So even such become as a prominent speaker, like as a prominent scientist like him, even he can say this fact with such diligence. Maybe we can accept that we are also some kind of a beginner in quantum mechanics. Anyway, so his main point is was to point the to attempt uh, was that to attempting to use the classical analogies. So, for example, our intuition, whatever we see around ourselves, whatever we feel around ourselves, how we see things, our intuition is based on that only. So, for example, if I ask you a simple question, what will happen if I throw a ball from here to there? All of you will be able to answer it without understanding quantum mechanics or without understanding any algorithm whatsoever. So you'll be able to say, okay, this ball will travel this much far. This will probably follow this kind of trajectory. Now, how do you know that? Because since you have born, like uh, uh, you have built your intuition throughout your childhood. Like you have that in your feelings. Like, okay, this ball will travel with this in this particular fashion. But in quantum domain, we don't get to visualize or we don't have the intuition to understand what is going on. So the only way to describe or the only way to know what is going on is by following the mathematical analogy. So which is I feel like probably the best way to understand quantum mechanics is you just understand mathematics step by step, and that clarifies a lot of things. So that's exactly what you have highlighted. So the behavior of the subatomic particles is fundamentally different from anything we experience in our daily lives. So which highlights that its principles are deeply counterintuitive and disobey our everyday experience. So as I said in the first talk, my agenda, I'd be speaking mostly about why we need Universe, what it is and how it works, and I'll be showcasing some live demonstration. And as students as well as researchers, what kind of educational and research value you can get from it. So I think these are the type of different quantum hardwares that are available right now. So one is superconducting qubit based quantum computers. Another one is a trapped ion based quantum computers, the photonic quantum computers, and neutral atom quantum computers. So there are other different kind of hardwares also available, but these are the mostly prominent and the famous ones. Now the major players of each of these superconductor quantum computers, are already mentioned, such as IBM, Google, Rigetti. In the trap time segment, mostly IonQ and Quantinum, and the photonic quantum computers, Xanadu, Psi Quantum, and the neutral atom quantum computers, it's QEra, Pascal, or atom computing. Now, the problem with different kind of hardware is that each of the quantum hardware requires its own SDK framework. So, for example, if you want to do or learn about superconducting qubit based system, you need to learn Qiskit, right? If you want to do understand, or let's say implement your algorithms into a ion trapped quantum hardware, so you need to understand circ. uh, Similarly, for photonic systems, you need to understand, or you need to have an intuitive, a very good grasp on strawberry fields, as well as in for the GPU based simulation, you need to have a good understanding about CUDA-Q. So that's where the problem is, that you have to master a lot of frameworks to really do quantum research in terms of algorithms. So as an algorithm developer, I don't feel like you should learn all of it, because most of your focus should be learning and developing those algorithms rather than learning different kind of frameworks. Of course, it definitely helps, but yeah. So learners and researchers must understand that multiple frameworks uh, to run the same kind of an algorithm in different hardware, which actually slows the process and creates a lot of confusion. So to gather more data, we actually, our team CDAC ran a big survey with around 200 participants. So we asked a different bunch of questions. The first question is, what quantum computing frameworks are you currently familiar with? So 57% people replied with, okay, we are mostly familiar with Qiskit. 8% replied that we are mostly familiar with Circ, and 12% replied that we are mostly familiar with Pennylen, correspondingly for CUDA-Q and other frameworks as well. Which shows that most of the students and participants were mostly familiar with Qiskit. Now, another question that we asked is, how important is it for you to have a single unified platform that integrates different quantum computing technologies? Now, 80% people have came up with a very strong support of it's a very important. Now, somewhere 20% people have told that, okay, it's somewhere important, and 1.5% people have actually said that it's not important at all. So as it came from you also, all of you, it's not an exception that how are you familiar with the fundamentals of quantum computing. So most of it just a beginner, even though yeah, most of them just are beginners. So which showcases in this slide also that around 70% people are just a beginner, 20% are intermediate, and 11% are just expert. Now, what are the different problems that we also try to understand that the researchers as well the students are facing currently? Now here's a distribution of it. Like, hardware constant is 15%, and talent and knowledge shortage is around 26%. Algorithmic challenges are percent, and other challenges that are also mentioned is also mentioned here. So now these are some of the surveys that we ran, and actually all of this helped us, or all of this kind of survey or kind of questionnaire helped us to or actually motivated us to develop Universe. So yeah, so this is the interface of the Universe. Now I'll go into it in a very details. I'll try to explain each and every single step, what it is, how it works, how you can get access of it. Yeah. So in short form, what is Universe is it's an unified platform redefining the way of developers, researchers, and enterprises engage with quantum technology. So as this is an integrated platform for designing, simulating, and executing quantum algorithms on classical accelerators such as GPU, FPGA, and vector processors, as well as we can execute this on multiple quantum hardware platforms. Now, these are some of the features of the Universe, which I'll explain in the upcoming slides also in details. So as I already mentioned that it allows you to write, you don't have to worry about learning multiple frameworks. So you can learn only one framework, and Quniverse will help you to write the same code for same kind of an algorithm in other frameworks as well. So as I said, it's an unified interface. It's a platform agnostic, which enables smooth operation across various quantum hardware. So whatever algorithm that you write, it actually we can integrate those kind of algorithms and execute those algorithms in either CPU, GPU, FPGA, or QPU as well. Yeah. And quantum SDK. So it is built-in libraries which let users quickly integrate on pre-made components into workflows, which actually improves the efficiency of researchers as well as the students. And we have also algorithm palette, where there are existing algorithms that are already there, which really which includes a lot of basic as well as some of the advanced algorithms, which definitely you will have a lot of help from that. And it's a hybrid classical quantum workflow. So you can just effortlessly integrate with major quantum providers and param HPC, which our CDAC is mostly capable, I feel like, um, which is high performance computing HPC supercomputers, to enable hybrid workflows, which can help you to combine quantum and classical methods effortlessly. And we also have various kind of tutorials which will not just only help you to understand those algorithms, as well as um, build your own intuition as well as do experimentation uh, in that platform. Yeah, with this I'll quickly go to Quniverse. So when you land the page of Quniverse, this is exactly what you land upon. So this is the interface of the Quniverse, where you will able to see a lot of different things, starting from what it is, a basic intuition, and some of the pictures of what is inside it, as well as some of the FAQs, what is quantum accelerator, such as what is quantum accelerators, what quantum simulators are supported here, as well as what quantum algorithm implementations. So once you get into this page, you need to have login access. So you can register for it. Yeah. So as I have already some login credential, I'll just quickly log into it. And upon login, so this is the interface it exactly looks like. So so there are a lot of things here actually. So I'll go each and every single thing one by one. So upon login, you will be able to see that there are some single qubit gates, multi-qubit gates, as well as some. So this is the gate palette. I think you can see my mouse cursor. So this is the gate palette, where there are single qubit gate, multi-qubit gates, as well as some advanced gates such as QFT, IQFT, which is quantum Fourier transformation or inverse quantum Fourier transformation. Now you have a blank circuit here, where you can drag and drop of various kind of quantum basis gates, such as Hadamard, X gate, Y gate, rotational RX, RY, RZ, C naught gates, Toffoli gate, CZ gates. These kind of gates, all you can add and create your own quantum circuit. Now uh, here so here you can name your circuit just for the future reference. I'm just for doing it for now, let's say I'm doing it for test. And here you can see the different kind of gates are available, so we can just drag and drop each and every gate. So as this is just a Hadamard gate, so as we all know that Hadamard gate creates equal superposition of the possible number of states. So as I said, as I applied the Hadamard gate on the first qubit, what it will do, it will create equal superposition of 0 and 1. So as this is a, okay, I can reduce the number of the, like how many number of the qubits as well as how many the classical registers I want, I can also manage that. So if I click on manage, so you can see here I can reduce the number of the quantum registers from 2 to 1 and classical registers as well. So yeah, which makes much more sense now. So if I apply a Hadamard gate, so as we know, the Hadamard creates equal superposition of both 0 and 1. So it creates a, here's a histogram of it, like you get 50% of 0 and 50% of 1. Now, just like in the last talk also, he mentioned some of the, he was talking about some Bell states, I think. So here you can also create some Bell states and check, yeah, sorry. Okay, I need one more qubit, sorry. Uh, yeah. So yeah, so which actually is a Bell state. So this is creates a Bell state of 0, 0 and 1, 1. Now on the right side, you get to see the custom code corresponding to this particular circuit. Here you can also create your own code, uh, such as this. Let's say, and it's also built in a very uh, uh, in a way such that if you do any kind of errors, that will also be visible. Uh, yeah. So you can create your own programming. You can create your own uh, coding, and it will create the corresponding circuit on the left side. Now, as I said, Quniverse is a unified platform which helps you to transform from one particular framework to another particular framework without putting so much of effort. So here you can see the open Quasam code, and you can directly convert it into Qiskit or Circ without knowing exactly in very depth what how to write the code in Qiskit or Circ or CUDA-Q or Quest, these kind of frameworks. So which helps you to write down codes for different frameworks. Now, yeah. So here is the probability distribution curve, probability distribution. So where you will be able to see what is the state, what is the probability of the output of my circuit. Now you can apply various kind of gates and do some kind of an experimentation with it. Yeah, and see how your state is evolving with certain amount of time. Right. So yeah, so that's exactly how it affects the basis gate, the basis states, and changing the probability of the basis states. Now here is one more cool feature, that is the debug feature. So if you click on it, you will be able to see in which step in my circuit what exactly my state is and how it is evolving with time. So let's say if I have a Hadamard gate, I want to know what is exactly happening after the Hadamard gate, and I don't want to know what is happening after all of the gates applied. So as I said, like this, after applying the Hadamard, I'll get this state, this probability distribution, and if I apply it a C0 gate, I'll create a Bell state. Yeah. So then again, if I apply a C0 gate, sorry, X gate, the changes will correspondingly accordingly. So this is a debug feature which will definitely help you to understand each and every step of your circuit and each and every gate what exactly it is doing and how it is changing your state, which I feel it's a very interesting and important thing for students like all of you, which will definitely help you to understand how a quantum circuit or quantum algorithm actually works in a much deeper way. Now here in the bottom side, you can see this is my circuit IDs, which is mentioned here, as well as you can see the status. Now one more thing, you can just extend it into fully expanded, and yeah, so this is the full circuit. You can do a lot of experimentation, and yeah, so probability, yeah. Mm, Wait. Yeah. So here you'll be able to see the different circuit IDs. So once you create your circuit, you just can, okay, and one more thing, without measurement gate, you cannot run your circuit. So you have to put the measurement gates to run your circuit, right? uh, because that's what measurement gate suggests. So it will run the circuit, and let's say for 10,000 times or for 10,000 shots or 1,000 shots, and it will create the histogram based on that. So here you will in that histogram you will be able to see how the probability distribution works. But when you actually run this circuit, uh, you will you will need the measurement gate. Without measurement gate you cannot run a circuit. So once you hit the run button, you will have a different kind of backends starting from CPU, GPU, and QPU as well. Yeah. So we have integrated the QPU of Super Stack hardware based on their API keys, and you can just implement your algorithms in CPU, GPU, and QPU as well. Now, if I just hit the submit button, yeah. So as I said, that this 10,364, this is my circuit ID that I have just submitted, and the current status is it's running. Once it's get done, it will have a green tick here. Now, it will take a bit of time based on the depth and the complexity of your circuit. Now, in the meantime, I'll describe the other features also. Yeah. So this is the quantum composer that mostly I described till now. So here you have a algorithmic palette where, as you can see, all the basic algorithms starting from some of the basic algorithms as well as some of the advanced algorithms are pre-built. So you can just load circuit and check the circuit and see how it exactly works. So in a sense, Quniverse will also help you to understand or create intuition about different kind of algorithms, and exactly understanding how the algorithms are actually working, right? So for example, yeah. So for example, if I pick a simple Deuce-Josh algorithm, I think all of you have heard about Deuce-Josh algorithm. It's one of the most basic algorithms. If I choose it for 2 qubits or let's say 3 qubits, and where if x0 suggests my either the function is balanced or constant function. So if I just if I hit the load circuit, so this is the corresponding circuit that I'll have. And if I hit the run button, submit, if I hit the run button, so again my job ID is been created and my circuit is been my circuit is been implemented. Sorry, my circuit has been executed in CPU as I have chosen CPU. Now I can see the status also. Here I can see the probability distribution of this whole circuit. Um, so it will take a bit of time actually, I think. So here you can see it's in Q, which some of the details of the circuit is mentioned here, which is circuit name is Deuce-Josh algorithm, and resources that I have used is QACC cluster, CPU based, and I am using Quasum simulator, and the status of it is queued. So that means it's still running. So if I hit a couple of refresh button, so yeah, you see I have got my output. So if you have some kind of an error, you will have the error here. So which I don't have any. So yeah. So yeah. So just the Dewey-Josh algorithm suggests that the state will be in 0, 0, 0. Now there are other algorithms as well, such as superdense coding, quantum Fourier transformation, quantum phase estimation, as well as some of the time evolution algorithms based on tautorization. So this algorithm I'll explain in details in the upcoming after lunch. So hopefully you will have a good understanding about it. Yeah. So these are some of the algorithms. Here are already implemented by our team CDAC. So you can explore all of them once you have the access. Now the next thing that I want to discuss is the job section. So yeah. So just I created this, I just submitted this job of Dewey-Josh algorithm just a couple of minutes ago. So here you can see the status of it. You can see all of the status of whatever the circuit you have ran till now. So yeah, so you can see all of them here. So this is actually says the Dewey algorithm is you can check what is the status is here from here also. Yeah, so I think which I have already said in the last segment. Now here's the documentation part. Now just creating your own circuit and making your own circuit uh, does not help you to really understand any algorithm from scratch. So for that we have written some tutorials, as well as we have written all of the tutorials basically, and the in-depth each and every single step of all of the algorithm that you have seen here, how it is working and what are the various steps are. You can explore those things here also. So just here in the introduction of universe, and then you will have building circuits, how we can build a circuit, as well as what kind of backend systems you are using. Yeah, and once you done with that, you can create you can understand the algorithms part also. So such as if I just a home button, okay. Mhm. Yeah, so in the QSDK section you have various kind of algorithms, starting from Simon's, Bernstein-Vezzarani, Dewey-Josha, Grover's algorithm, quantum teleportation, and all the algorithms that you have seen there in the palette. So all the tutorials are available here. So by reading all of this and by starting to understand uh, uh, all of this, you can have a much more deeper understanding about each of this algorithm. For example, if I just click on, let's say, quantum teleportation, or uh, let's say let's go with a very simple one, Bernstein-Vezzarani algorithm. So you can see the tutorial is already available, and if you have some kind of a difficulty understanding about it, so there is some short video clip also available, so that you can build a hands-on intuition.